We all know how the software development process works, right? It's pretty simple. You get yourself a compiler and a linker and a debugger, throw down some open curly braces, and start laying down code. But what if the thing you're writing software for isn't a normal computer? What if it's an embedded thing inside a toaster or an IoT device or something? That complicates things quite a bit. And then, what if it has more than one processor? And you need to optimize the code to run in parallel. That's yet another challenge. And finally, what if those processors are different from each other and you need to partition your application to take advantage of those differences? Well, that's a whole nother kettle of fish, isn't it? Hi, I'm Amelia Dalton, host of Chalk Talk. If you're dealing with heterogeneous, multi-core embedded systems, you're gonna need a suite of tools that can handle that kind of action. My guest today is Felix Baum from Mentor Graphics, and he's going to chat with me about Mentor's comprehensive suite of tools that address this challenge. Before we get started, remember to click the link. There you can download a free white paper that further expands on this topic. Hi, Felix. Thank you so much for joining me today.
Well, thank you for inviting me. Nice to be here.
Okay, so software development isn't quite as simple as it was back in the days when our systems had just one processor, right? So what market forces do you think are driving the kinds of architecture changes we're seeing in our systems today?
That's a great question, Amelia. There are three key trends that are driving opportunities and creating the challenges for the systems. First and foremost is the market's becoming more and more competitive. The pace of innovation and global competition is rising every day.
Okay.
We see a lot of devices being consolidated, where in the past you used to have a standalone refrigerator, a standalone dishwasher, and things like that. These days, folks try to consolidate a lot of these technologies and capabilities, where you have a refrigerator with an LCD screen that has apps running on it and tells you when it's time to buy milk.
Right.
And to put systems like that together, what you have to do is try to reuse as much software as possible. And when you're designing systems like that, you always have to worry about space, weight, and trying to make sure that your device consumes less power. Because of that, you try to bring in various different operating systems and complex configurations. We also see a lot of advancement in technology of designing chips and SoCs.
Okay.
Folks used to have one core, two core designs. Nowadays, there are multiple cores of the same type, and even newer devices where folks, SoC vendors, design chips that have a plethora of cores that are specifically designed for a particular task.
Right. When I started off, systems only had one core.
That's right. That used to be the case when folks used to develop technologies and build devices for purpose-built devices. You would pick a core, a specific embedded core like an M4 that are plenty available today, and build your tablet and build your camera or build your access point.
Right.
What we see lately is availability in devices that are used today, multiple cores are being used.
Yeah.
And you see things like PlayStation, spacecrafts, and even cars and airplanes these days being built based on these multi-core chips, multi-core SoCs. And again, there are just multi-core SoCs that are kind of homogeneous, where they all use the same cores. And then there are others that have heterogeneous cores, where you have two big cores that are very powerful and a plethora of little cores to do sensing and to do some real-time tasks and things like that.
So Felix, you talk to a lot of companies developing complex systems. Now, how do you see applications being developed for this big range of architectures?
Thanks, Amelia. So let's briefly talk about how these systems typically developed. For example, if you look on the left side of this picture, you'll see that we have a patient data acquisition devices, and I noticed that you're wearing a fitness watch. Well, the device like that has one purpose in life, which is capture your heartbeat and track how many steps you're making.
Right.
So it has to be very fast, it has to be very reliable, and what most important for the software developer is that that device cannot afford any jitter.
Right.
Meaning that if I'm measuring how many heartbeats you have a minute, it better take measurement every 60 seconds, not 58, not 62. Otherwise, it's completely useless. So what we see in many instances, what people try to develop and design things like that, they care for real-time performance, they care about determinism, and sometimes and we see instances where they just write application from scratch without even using operating system, not to pay any performance penalties.
Right.
On the other side, if you are looking at a cell phone, for example, or a patient monitor in a hospital, people expect to have a rich GUI, rich IDE, very nice animation. And when we look at the devices like that, these days we see a lot of folks deploy Android or Linux-based applications on devices like that, on a bigger processors like that.
Yeah.
Now, if we go look up all the way to the right side of the slide, what you have here is an enterprise-based device. So you build a device, it goes into IT space, or these days it's quite popular, cloud infrastructure. And what you need there is you need to support a lot of networking protocols, you need to support web servers, web browsers, and things like that, an IT kind of infrastructure to support those applications.
Yeah.
And we see a lot of Linux and Unix-based design there. And again, those applications use different features and have different requirements.
And now, we're seeing all of this complexity in a single semiconductor device, right?
Well, absolutely. So let's just take a device like TI OMAP 5 that has been manufactured by TI and sold on the market today. What you have is you have TI that design one single SoC, and in that one body that is less than the size of the quarter, you have two Cortex A15 cores, you have two Cortex M4 cores, and then you have another plethora of other little controllers here and there for the I/O, for the security features, for the GPU and others.
Sure.
And all of these capabilities now, again, as I said before, fit within a quarter.
So with all of these different processors in the same environment, how do you decide which software runs where? It seems like there would be a lot of permutations.
That's correct, Amelia. And this is one of the areas where we struggle a lot as software developers, and I used to be one as well. If you simplify this environment and just take two cores for simplicity, you can run one operating system on cores, whatever it's a Linux or real-time operating system. Or you can mix and match just to make your life more interesting, where you can have two instances of Linux running side by side, or mix it up and have a Linux and a real-time OS running side by side. Again, it all depends on what it is you're trying to build, and that will dictate which operating system and where and how you want to deploy it. So in general, with just two cores, there are pretty much 8 use cases, 8 configuration choices that you might go after. Now, to make things a little bit more complicated, we've seen a lot of times these days with virtualization getting into the embedded devices, folks like to deploy on top of hypervisor. Again, there are a couple very good reasons why you want to do that. And if you bring in hypervisor in a picture, then there are another 6 use cases that we see folks deploy with. Now, taking it all together, if you just have 2 cores, you have 14 use cases of variations where you can deploy a real-time operating system or Linux or an Android on a 2-core device. If you go for devices from TI or Freescale where they mix and match cores, let's say in this case you have 2 Cortex A15 and 2 Cortex M4 cores, you have another 2 cores that can run an operating system, and it's up to you as a developer of your particular device to determine what you want to run there. And then, of course, if you go and look at a FPGA, then possibilities and configurations are endless, because you can instantiate soft cores and then again add those and determine which application gets to run there. So as you can see, there are very many different things that you have to consider as a system developer.
Wow, that is a lot of permutations. So I assume that developing software for these things, the normal embedded software development challenges I'm used to, are still going to be around, right? And I assume there's going to be a whole lot more new ones?
Well, absolutely. Everything that you had to deal with when you work on a single core still stands, except the systems of today are so much more complicated. Where in the past you have to worry about how to boot your device, how to configure your device. Well, now imagine that your device used to be one board in a system and you had a couple other boards, for example, if your device was complicated enough. Now all of that collapses into one SoC, one chip. So you still have to determine your system architecture.
Right.
How do you lay out your peripherals, where your system gets to run, which operating system gets to control which peripheral and which resource. You still have to configure all the system and be able to go and do your favorite build and linkage stages, where at the end of the day, you want to produce your binary, so you plug it in, turn it on, and your device boots.
Right.
Booting is another thing that you still have to worry, because in the past, you only have one core, you turn on the power, that core boots with an application that you put there. Well, now you have multiple cores, and it's up to you to determine which one gets to boot first, which one gets to boot next, and some of the reasoning behind the booting sequence has to do with maybe regulations. If you are building a car, and you have a backup camera, there are only 2 seconds from the moment you start an engine and you put your car in reverse till the moment the image is appearing on your LCD in your car. So you have to make sure that your applications are booting fast enough.
Sure.
Debugging. Well, imagine that you have all this complex system now and you need to debug all these different operating system running on all these different cores. And I think at the end of the day, what we see folks struggle with is once you get to the point where you can debug the whole thing together, folks kind of take a step back and go through separation. Well, gee, if I just separate these things, if I take and break things and break dependency, it would be easier for me to debug things. It would be easier for me to develop things. And we see a lot of folks kind of go through this process of separation. Other folks look at separation from the purely reliability standpoint, where if you have a capability that needs to be fast, if you have a piece of software that needs to be reliable, you want to separate it away from Android, you want to separate it away from Linux and other unreliable, so to speak, operating systems, and you want to run it on a dedicated core.
Oh, okay.
And then, of course, if as soon as you separate things, you run into an issue of device sharing. I have 2 kids. I can take them into a room with plenty of different toys, and it's just a matter of seconds until they both decide to play with the same toy.
Right.
If you have an LCD screen, if you have an Ethernet port, if you have a serial port, it doesn't really matter how many cores you have and how many operating systems you have running. At the end of the day, you might want to share that one display.
Right.
And sharing of the resources is a complicated task. And of course, interprocess communications and security aspects also come to play here and need to be addressed.
Okay, now Felix, I see that your business card says Mentor Graphics, so I bet we should talk about how Mentor has some solutions that are going to help me address these challenges, right?
Well, we are trying to help our customers to solve these issues and to simplify this complexity. We are not in a position to come in and tell customers how to design their device. What we try to do is we try to put together a comprehensive framework that allows our customers to deploy using all these different configurations.
Ah, okay.
So our framework allows for them to configure and deploy these various operating systems on various cores. Our framework allows them to determine the boot sequence and the boot timing and resources, how things get to boot in a right order, in a right time frame, and how they can set up their devices and their cores and applications to talk to each other and communicate with these various cores. Of course, all of that is happening inside the device and with a zero or no visibility into it. So we have a complete set of tools that can utilize to be able to go and see how your device is booting, how your device is working, ability to set breakpoints and visualize all of the interaction between different pieces of the software.
Okay, great. Let's dive down into a couple of the examples that you were talking about. Now, one of the things you just mentioned was interprocess communication, and that would be a big challenge in these systems. Tell me what you can do for me there.
Of course, thank you. What we have done is we see a lot of folks struggle with trying to come up with a framework of how to communicate between various distinct pieces of software.
Yeah.
Some folks invented their own methodologies, their own technologies. What we've done is we noticed that these days, with Linux making a big strides into the embedded space, we decided not to invent our own wheel.
Excellent.
We looked at the concept and constructs that Linux is using today, such as VirtIO, Remote Proc, and RPMessage. And we extended these capabilities to accommodate not just applications running on top of one Linux operating systems, but we extended it to allow for this multi-core heterogeneous systems. What we also have done is we've created a clean room implementations of these concepts and constructs, and we provide it to our customers. So one can indeed take all these frameworks and hook it up to their own favorite operating system or bare metal applications and make sure that they talk to each other. So Linux can talk to Android, Android can talk to bare metal application, and bare metal application can talk to your favorite real-time OS.
Okay, cool. That kind of gives me a universal plug and play between all my processors and all my different configurations. But one question comes up for me here. With all of these different cores in my system out there doing all these different jobs, who plays traffic cop? Who keeps everybody in line, Felix?
So what we have is we extended concept of the master OS, and
Okay.
what we've done is in many instances you might want to run an operating system on any core and then be able to dynamically go and start other operating systems running on other cores.
Right.
So the framework that we put together allows for that specifically.
Okay.
In the past, Linux again had construct to be able to go and launch an applications running on top of the same Linux instance. What we've done is we extended that, and we're allowing you to run an application on Linux or bare metal or RTOS and be able to spawn an OS on a next core side by side to it and be able to load that payload and execute it. And then once it's done doing whatever you want it to do, to be able to go shut it down and maybe load a different applications to run.
All right, I get the kinds of problems we're solving here, but can you tell me a little bit about how we'd use this in our system?
So let me offer you a couple use cases.
Okay.
Let's just say that you're building a system that's going to go into the building and control elevators.
Sounds good.
Or you're building a system that goes into the hospitals. And a lot of these systems, for the most part, are off.
Yeah.
I mean, if you go look at the building, there's nobody enters the elevator at night.
Right.
And what we see a lot of our customers when they build these devices is they're trying to conserve power and save power. One of the ways to do it would be to have a dual core device where on a first core you run a bare metal application or a real-time operating system that does nothing but checks sensors and checks what time of the day it is. If it's morning or if someone wakes up and walks up to the elevator, you might want to go and dynamically load Linux to run on the next core. Linux will come up. It will control, for example, an LCD screen that will show you the buttons and allow you to go push that button and go to a particular floor. When it's evening and there are no more customers to walk up into the elevator, you might want to go and to conserve power, prevent Linux from running on that core, shut it down, conserve power, and then kind of go back into your RTOS running on a single core, doing its own thing, conserving power and doing things like that.
Gotcha.
Another use case that we see a lot is offload work,
Okay.
where you might run Linux, for example, on a core or an Android on a core, and someone might hand over a video file or encrypted data to you.
Okay.
Well, one thing that, of course, you can do is you can run decryption algorithms or digital right management algorithms on top of Linux.
Yeah.
That might expose your algorithms, that might expose your keys. So we see a lot of time where developers like to go and protect that.
Yeah.
Go run it somewhere separately where nobody can hack into it, nobody can steal these algorithms and keys.
Right.
Well, the perfect solution here would be you can take your decryption algorithm, you can spawn a real-time OS or bare metal to run on a secondary core. That core would come up. That core would come to you as a Linux application and say, hey, what do you want me to do?
Okay.
You hand it over the file and you say, here's the file for you. Here, go decrypt it and put it somewhere in the memory.
Nice.
And let me know when you're done decrypting it. That little core or little OS would run, execute it, do everything that it needs to do, completely protected, completely isolated and separated. When it's done doing the work, it will come back to you and say, I'm done. What do you want me to do next? And this is where, again, your Linux application can say, well, here's the next file for you to go decrypt, or it might reboot that core and say, here, now I want you to do something else, or here, go do some other offloading task for me. So these are just two use cases that we see folks deploying systems with.
Okay, cool. I understand what you're saying about these use cases, about the technology and the framework, but can we step back a level just a second, and can you walk me through an example of what this looks like from an end user perspective?
Absolutely. So here's, Amelia, a use case that, again, we simplified, and just to prove a couple points. Looking at the devices that one might find, for example, in the hospital.
Okay.
You might have a device that is monitoring the patient and checks for the patient's heartbeats and doing some data acquisition. If you are doing data acquisition, again, the performance, the real time, the determinism is really, really important. And you want to make sure that the application runs fast and that application never gets interrupted. Now, when you have these devices, again, most of the time they have some kind of display. And these days, folks expect this display to be nice. They like to see nice animation, maybe some 3D stuff going on.
Yeah.
Again, a lot of folks get spoiled by cell phones these days, whatever cell phone is an Apple, iPhone, or an Android. You tend to expect these days that these devices will have rich graphics. Again, it doesn't have to be fast, but it has to be rich, it has to be user-friendly, and it has to be reliable.
Right.
You don't expect to go walk in the hospital or a building, if this is an industrial device,
Right.
and have the display flicker. And then, of course, what we also see in the hospitals these days is a lot of instances where maybe it's you remotely, or maybe it's your doctor who wants to, from his office, log into the system and see if their child or if their elderly parent is doing okay. Maybe it's a doctor who wants to log into the system and monitor the patient progress. But we see a lot of times people build these devices and enable remote access to them.
All right, Felix, we're engineers here. Take me under the hood with this example.
Sure. So again, going back to the original device that I showed you earlier, let's just pick one of these heterogeneous multicore devices that has two A15 cores and it has an M4 core. What we did is, for reliability reasons and security reasons, we run a hypervisor on top of these two A15 cores.
Okay.
With a hypervisor, we can isolate operating systems and very easily reboot them and dynamically bring them down and bring them up.
Okay.
We have two instances of Linux running side by side. First version of the Linux is there just to run a web server and be able to grab the data that is being displayed on a display and serve it remotely.
Okay.
That way, someone from their office, whether it's a doctor or a relative, can see how the patient is doing. And if, God forbid, a hacker decided to hack into that device over the web interface, it is very easy for us to collapse that Linux instance and restart it because we have it running on top of hypervisor.
Ah, okay.
The second Linux instance that we have there is running there to control GPU and the display. Again, in the demo that we have is we tend to expect a really nice rich graphics IDE, so we're running Qt system, Qt graphics, and be able to go and display heartbeats and other patient-relevant data. And then, of course, when you boot up the system, what that version of the Linux is doing is it launches on a real-time OS on an M4 core that is part of the same SoC. And that's the core, and that's the OS that actually monitors the patient and actually collects the patient data. Again, we have JTAG tools to debug all the system. We have other tools to visualize the system performance and be able to optimize graphics packages and network throughput in our demo. And what we can again do is show you how, if you break into the system and if you hack into the system via the web interface and bring one of those virtual machines down, the RTOS running on M4 core or Linux running on top of hypervisor that controls the GPU, they're unaffected, they continue to run safely side by side, and all of these pieces of the software that I just described working together with this framework that we help to put together for our customers.
All right, cool. Now, I understand that you have a video demo that goes into much more detail on this, so we'll put a link here up on the screen right now so people can watch whenever they want to, and we'll include one at the end of the broadcast as well.
Thanks, Amelia. That's a wonderful suggestion. The screenshot here that we have is just shows some of the grabs from that video to highlight how our tools can help you to debug every single bit of software that's running on the system.
Nice.
We have a diagram here that shows how you can visualize the system behavior and watch, for example, that Qt application running on top of Linux in one virtual machine is being affected by some other interrupt running on a M4 core that runs on a real-time operating system. Again, I highly suggest folks to click on the link and go check out that video.
You've been describing kind of a framework type of approach to these solutions. Now, can you give me the big picture on what Mentor offers in this space?
Absolutely. As you might be aware, we have a real-time operating system of our own. We have Mentor, embedded Linux, and one of the reasons why we put this framework together is we see customers that would go and deploy our Linux or use our Android expertise on a big, large course, and then come to us and try to run Nucleus RTOS on a little course. And we have a few other tools as well. So yes, we offer customers framework that we put together, but we also offer them a complete solution that includes their RTOSes, the Linux, the Android expertise, and tooling to help to bring it all together.
All right, Felix, I think I may need another round of coffee. This has been a bit much to take in today. Can you recap just a bit for me?
Absolutely. I think that is easy to understand that we are living today in a world of multi-core devices. They are more and more complex, they are more and more sophisticated, and they are more and more networked. And unfortunately, and I'm sorry to tell it to your listeners, there is not a single bullet.
Dang it.
There is no one button that they can push to take their SoC, to take their hardware, and just lay out their application to take full advantage of this multi-core design. And that's where we come in, and we are here not to tell you how to solve your problem. We're here to offer you all the pieces and all of the tools with a framework that you can use to put together and design your device. to design your device to be reliable, to design your device to be secure, and to design your device to be robust, which is
Excellent.
what is really important in this world of multi-core devices of today.
Well, I think that was all I have time for today. Thank you so much for joining me, Felix. It was a pleasure speaking with you.
Thank you very much, Amelia. Nice meeting you.
Before we go, don't forget to click that link. There you can download a free white paper that further expands on this topic. For Chalk Talks, I'm Amelia Dalton. For more Chalk Talks, check out the EE Journal YouTube channel or the on-demand section of eejournal.com.